Hello everyone, this is Dr. Yuzo, and today we're gonna continue our lecture with Module 4, Thevenin's and Norton's theorems. So according to the Gantt chart, we can tell this module is about additional circuit analysis tools. So once again, nodal and mesh, and thus the KCL and KVLs are always the most important ones and always sufficient to solve any given circuits. Okay? Please keep that in your mind. And then let's talk about the Thevenin's and Norton's theorems. So in this module, we can learn first the motivation, what these theorems for. Second, talk about the concept, what they are. And then we're going to discuss how to conduct it. Okay, we have a procedure. And then we're going to talk about a very useful and practical theory about maximum power transfer. Okay, the last but not least, we're going to go through several examples to really conduct the Thevenin and Norton theorems. Okay, let's start. First, what is the motivation for us to use them? Okay, let's see, given a complicated circuit or say network like this, it's complicated enough. Actually, you can tell it is including many transistors and op-amp and bunch of resistors. So to this guy, if we want to study voltage, current, or power of one particular load resistor, for example this guy, then Thevenin's and Norton's theorems can help us replace the entire circuit network exclusive to that particular load resistor by an equivalent simple circuit. What it's talking about is basically, since we only care about this resistor, and then we just replace all the rest of the circuit, these guys, into a simple circuit, so-called, like this. Okay. You see, the rest of the complicated circuits are gone. Instead, we have equivalent simple circuit to feed this particular load. So basically, Thevenin's and Norton's theorems are for us to simplify substantially the circuit. So further explain the concept, what are they? So if we examine any part of the circuit network from a pair of terminals, with respect to those terminals, the rest of the network is equivalent to a simple circuit. What is simple circuit? Simple circuit consists of one independent source and one resistance. Again, going back to the previous slide, we are seeing the original complicated circuit like this. However, since we only care about this particular resistor, so two terminals cross it, and then we make all of the rest of the circuit to become a simple independent source and one resistance. We could have two options here. Option A, the simple circuit consists of one independent voltage source series with a resistance. And this option is called Thevenin's theorem. And option B, the simple circuit consists of one independent current source and parallel with a resistance. This is called Norton's theorem. It's not surprised that option A and option B are equivalent to each other, since both equivalent to the given original circuit. Okay. However, be careful. The given original circuit, including this resistor, and Thevenin and Norton's theorems are trying to replace all of the rest circuit exclusive this resistor. Let's see a more viralized explanation of the concept. To option A, we can see first the given original total circuit is highlighted by yellow. consists of part A and part B. If you want to find the equivalent Thevenin or Norton circuit, we need to first of all identify who is part A and who is part B. Part B is the part you want to keep. For example, the resistors in previous slide. Part A is the part you want to replace by the simple circuit, so-called. So, like the previous slide's complicated part. And their connection obviously is two terminals, A and B. So given a problem, you first of all need to clarify who is part A and who is part B. And then we're gonna go ahead to find the Thevenin or Norton equivalent circuit. To Thevenin option, we keep part B without touching it at all. And then cross terminal A and B, we find the equivalent Thevenin circuit for part A. Norton is similar. Keeping part A untouched, cross terminals A and B, we are looking for a Norton equivalent circuit for part A. So part A becomes a series connection between an independent voltage source and resistance for Thevenin, or part A becomes a parallel connection between the independent current source and resistance, like this. So Thevenin and Norton, respectively. Once again, part B remains same. So next, let's talk about the relationship between the Thevenin equivalent circuit here and Norton equivalent circuit here. As we have said, they are equivalent to each other since both are equivalent circuit of part A. And then the relation is very straightforward. So first, Thevenin resistance here, RTH, is equal to the Norton resistance, R sub n. Second, the Thevenin independent voltage source is equal to the Norton independent current source current times the resistance here or here. They are the same. So apparently these two equations are about a simple Ohm's law. Now let's talk about how to really conduct Thevenin or Norton. Okay. Once again, since they're equivalent, so we just need to find the Thevenin or Norton, and then the other one is pretty straightforward. So here I'm providing a procedure for us to conduct finding the Thevenin equivalent circuit. Okay. So step A, what we want to do is remove part B. Of course, before step A, you need to identify who is part A, who is part B, so-called. Okay, and then we remove part B and find the open circuit across those two terminals, which is nothing but our independent Thevenin voltage source voltage. So open circuit voltage equals to Thevenin voltage VTH. Step B is optional. We will see what it's for. Okay, jump to step C here. So find the, obviously, resistance. We can call it Thevenin's resistance. How to find it? Here, be careful. We have three possible scenarios. We can call them as case I, case 2, and case 3. Case I. If part A has only independent sources without dependent sources, what we can do is we can zero all the independent sources and then find the equivalent total resistance across those two terminals here as our RTH. To case 2, if part A circuit has only dependent sources without any independent source, we have to add a independent test voltage source, we call it V sub t, across the two terminals, and then calculate the current I sub t through the two terminals, and then the Thevenin resistance is equal to the ratio between these two. You can tell that is a little bit more complicated than case 1. Last, case 3, if part A has both independent and dependent sources, which obviously is generalized case, then what we need to do is find I sub SC. From the subscripts here, we can tell it means is short circuit current, and then the Thevenin resistance equals to the open circuit voltage divided by the short circuit current. And how to find the short circuit current? We need to go back to step B. So step B is replace part B by a short circuit. Okay. Here, be careful. To find the Thevenin independent voltage source voltage, we need to open part B. To find the short circuit current here, we need to short part B. So now we got VTH and RTH. And then the last step, D, is the entire circuit network is eventually equivalent to as described in page 5. Part A is replaced by one independent source and resistance. Part B remains same. This is the page 5. Okay. Entire circuit equivalent to Thevenin or Norton equivalent circuit connecting to the part B circuit, which remains same, untouched. And another thing I need to remind you is in step C, case 2 here, you probably can realize that since no independent source, what is the VTH? The answer is VTH is just a 0. No open circuit voltage. Then the Thevenin equivalent circuit is just one equivalent resistance, RTH, without independent source. Another thing I want to remind you guys is case 3 method obviously works for case 1 as well, because case 3 is more generalized case. Next, about the maximum power transfer. It is stated as this. So the load power reaches max when the load resistance is equals to the source Thevenin resistance. So what it's about is how to choose a load to achieve the maximum power output. This is what this is for. However, be very careful here. You are achieving maximum power output. It doesn't necessarily mean you're achieving the maximum efficiency. What is efficiency? Efficiency is equals to the output power, which is the load power, divided by the source power. So output over input. This is the efficiency concept. So maximum output power is not equals to the maximum power efficiency. Then the obvious question is, what is the efficiency when maximum power transferred? In other words, since we are saying the maximum output power is not inducing a maximum efficiency, then what is the efficiency then? Okay, let's take a look at the calculation. Okay, we are seeing a circuit like this. So the source is VTH, and it has a Thevenin equivalent resistance RTH, and feeding a load RL. Here. So we are saying first the maximum power output means our RL is equals to RTH. Okay. Then let's see what is the power then. PL equals to what? Is equals to VL squared divided by RL, right? This is the power equation. But what is VL? Look at the circuit here. This is a simple single loop circuit. Total VTH is shared by RTH and RL. And RTH is equals to RL. So apparently VL is equals to half VTH. And then let's talk about the source power. How to find the source power? Source power equals to the VTH times I. By I mean the current flows through this loop, which is also the current feeding the load. It just equals to VTH times, according to Ohm's law, it equals to this, right? So I equals to Ohm's law, and then it equals to VTH squared times 1 over 2RL, since RTH is equals to RL. So combining these two results, we are finding the efficiency, which is equals to, again, PL over PS, output over input. And then what is the result? So according to this ratio, and then we substitute PL and PS respectively by these two results, you can find the efficiency at maximum output power, which is turned out to be 50% efficiency. So the conclusion is, repeated again, when you achieve the maximum power output, here, you're only receiving 50% of the efficiency. There's no free lunch. You're basically achieving one goal by sacrificing another one, because 50% efficiency of power is terrible, as you know.